Hello everyone, this video is about an FET with the source tunneling barrier showing suppressed short channel effect for low power application. Myself Karanya and my team members are Adira and Navageetanjali of ECE 3rd year from Tyagarajar College of Engineering, Madurai. The topics that we are going to cover is introduction, quantum mechanical model, result and discussion, graph and conclusion. First of all, if we see the physical dimensions of a FET, the short channel effect related issues have become the main challenges, which includes drain-induced barrier lowering, VTH roll-off, junction punch-through, and direct source-to-drain tunneling. And for reducing the negative effects of short channel effect, we can minimize the channel thickness and by introducing counter-doped pockets at the deep source channel and drain channel. And in this paper, a device design technique using tunneling barriers for reducing the short channel effect is being proposed by introducing tunnel barrier at the source and drain junction of the silicon FET. The threshold voltage roll-off can be significantly suppressed. This is because the tunnel barrier weakens the electrical coupling between the drain bias and the transmission spectrum in energy. This paper further reveals that the tunnel barrier at the source junction dominates the physical mechanism, minimizing the short channel effect of the tunnel barrier FET. And thus, the device performance can be improved appreciably by removing the tunnel barrier at the drain side and by decreasing the tunnel barrier height at the source side. And to further improve the electrical performance, we investigate a device design technique with ultra thin and sharp potential barrier at the source drain junction.
So far we gave an overview about the things discussed in this paper, and now we will be giving a brief presentation about what is discussed and what they are tending to tell in this paper. So here are the index terms which is used in this paper. First of all, starting with short channel effect, then drain induced barrier lowering and threshold voltage roll-off. So when we scale down the physical dimension of a FET, short channel effect related issue tends to become significant, which may be like drain induced barrier lowering, which is nothing but tending to reduce the threshold voltage of the transistor at high drain voltage. And what is meant by this threshold voltage is that decrease of the threshold voltage with decrease in the gate length. So these negative impact of a short channel effect can be mitigated by reducing the channel thickness and introducing counter doped pockets at the deep source channel and drain channel junctions. So it helps to reduce the short channel effect as well as lowering the off current. In order to improve the electrical performance, we investigate a device design technique with ultra thin and sharp potential barriers at the source drain junction. So next, we have the quantum mechanical model. This quantum model shows the stimulated device with heterogeneous SD junctions, which is nothing but source drain junction, and energy band diagram at the heterogeneous junction. So what is meant by this heterogeneous junction? It is a junction between two semiconductor materials with unequal band gaps. As the width of the silicon body increases in nanoscale, which may be around 5 nanometer, the quantization impact on the silicon electronic band structure can be considered. So this diagram you are seeing at the right can illustrate the band diagram of a simulated two-dimensional silicon tunneling barrier FET with effective barrier height of psi about 1.42 electron volt and 1.29 electron volt for a width of 5 and 3 nanometer size. So this quantization depends mainly on the bandwidth, and electron effective masses are also extracted, and the graph which I will be showing in the next slide would illustrate that. So here you can see the graph of the band diagram, quantization dependent band gap, electronic effective masses and all. So these were the things discussed in this paper in brief.
So here we are going to detail analysis about the result and discussion of our paper. So this figure shows the transfer characteristic of the silicon FET and the tunneling barrier FET with various heterojunction condition at different drain sources voltages. So this first graph shows that the double barrier TB FET shows less bit differences between two different VDS values. So this B and C graph shows the single barrier source SBS TB FET exhibits less than the single barrier of the drain. So finally, the width roll-off devices the channel length decreases. So these are some graphs which are inferred in our paper. So first, this picture that infers the electronic band structure of silicon slab terminated by hydrogen atoms on the surfaces, where the band gaps and curvature effective masses can be determined by the dou and delta points which are shown in the figures. So band gap curvature effective masses, the two lowest subband energies, and the electron affinity differences with respect to the bulk values with various WB values. So the next graph gives the lowest subband profiles of the FET and SBS TB FET. This graph is a shifted transfer characteristic of the FET and SBS TB FET with the effective barrier height phi. Then this is a drain current of the SBS TB FET and the width roll-off between the devices with plotted against phi, where the drain currents are stimulated with a gate overdrive. So this final one gives the energy resolved local DOS along the channel of the double barrier SBS TB FET, and the these two potential lines represents the lowest subbands corresponding to the m power lambda and m power delta. Energies at the zero represents the electric field of the source region. So coming to the conclusion, the ultra-thin potential barrier at the source junction of the resonant tunneling FET has been shown to be able to alter the transmission spectrum to reduce the impact of channel potential, and the channel potential variations is due to different VDS values on the drive current. Then the TB height serves as a trade-off knob between on-currents and immunities of the short channel effects. So this paper provides an additional feasible option to suppress the short channel effect of the nanoscale devices for low power applications. So finally, thank you for watching our video. Thank you.